Nearly 3 billion miles from the Sun, a giant world spins in near total darkness, battered by winds 4 times stronger than the worst hurricane ever recorded on Earth. You want to land there. Neptune has no ground to catch you, no surface to stand on, only a thickening ocean of gas that turns to liquid, then to something scientists still argue about. Somewhere down there, it might be raining diamonds. Today, we travel through storms wider than our entire planet, past a moon spiraling toward its own destruction, and into a pressure that could crush a submarine like a soda can. If you enjoy the ride, hit like and subscribe. It helps this channel keep exploring the solar system with you. Hold on. We begin the descent. Before your ship reaches the clouds, you need to understand what you're actually flying into. Earth is rock. Mars is rock. Even Jupiter, the biggest planet of all, is mostly hydrogen and helium, the same light gases that fill a birthday balloon. Neptune is different. Underneath its calm blue face, it hides water, ammonia, and methane, squeezed into a slushy, super-hot layer that scientists call an ice giant. That word confuses people at first. Ice giant does not mean frozen solid. Picture the ice cubes floating in a glass of soda, then imagine crushing them under pressure so strong they stop acting like ice at all. That is closer to what waits inside Neptune, a mix of water and gas forced into a strange, in-between state that does not exist naturally anywhere on Earth. It behaves partly like a liquid, partly like a solid, and partly like nothing scientists have a simple name for yet. Your ship's instruments begin reading the outer atmosphere now, mostly hydrogen and helium up here, thin and quiet, almost peaceful. That peace is a trick. It is the last calm layer before the planet shows its true nature. Uranus, Neptune's twin in size, gets grouped into the same ice giant category, and together the 2 planets form their own class, separate from the small rocky worlds near the Sun and the massive gas giants farther in, like Jupiter and Saturn. Neptune sits at the very edge of that boundary, colder and stranger than almost anywhere a spacecraft has ever travelled. A scientist who studies planetary interiors once compared Neptune to a layer cake nobody has ever tasted. From space, all anyone can see is the frosting, a smooth, glowing blue shell. Nobody has ever reached the layers hidden underneath, and every model of what lies down there is still an educated guess. Your ship pushes deeper. The hydrogen thins out around the hull. Faint traces of methane begin showing up on the sensors, the same gas responsible for the colour you saw from far away, a deep, glowing blue, unlike any other planet in the solar system. That colour is not decoration. It works like a warning label, written across the entire sky. The temperature outside your hull is already dropping past anything a human being has ever survived unprotected, and you have barely started falling. Engineers back on Earth built this ship using the best guesses available, based on decades of telescope images and a single brief flyby decades ago. Nobody has ever tested a hull against the exact conditions waiting below, because nobody has ever sent anything this deep into an ice giant before. Every reading from here forward writes a new page in a book that barely has a first chapter. Every mile down adds more pressure, more heat from friction against the hull, more unknowns your instruments were never fully built to explain. Somewhere beneath these clouds, according to the best models scientists have built using math and lab experiments, there might be an ocean unlike anything else in our solar system, and inside it, carbon crystals raining down like snow made of diamonds. Nobody has confirmed that firsthand. No ship has ever gone deep enough to check for certain. Your ship is about to become the first, and the outer clouds are already rushing up to meet you. Before you cross into them, look back for one last second toward a tiny point of light behind your ship. That point of light explains everything about the world you're falling into. That tiny point of light is the Sun, and from here it looks barely brighter than any other star scattered across the sky. Neptune sits nearly 3 billion miles from home. To put that in a picture you can hold in your head, If the sun's light were a race car, it would need over 4 hours just to reach this planet, compared to about 8 minutes to reach Earth. Sunlight this far out arrives weak and thin, around 900 times weaker than what warms your skin on an ordinary summer day back home. Noon on Neptune looks like a deep, heavy twilight, the kind you get minutes after sunset, except out here it never brightens again afterward. This distance shapes everything about the world you're about to enter, far beyond a simple number scientists record in a chart. Weak sunlight should mean a cold, sluggish place, wrapped in a slow, quiet atmosphere with little energy to power any real storms. That assumption is about to be proven completely wrong. Despite receiving almost no warmth from the sun, Neptune hosts winds far stronger than anything ever recorded on Earth, tearing through its atmosphere with a force sunlight alone could never explain. Something inside this world generates energy of its own, and scientists are still working out exactly what that hidden source might be. Your ship continues its approach, gravity taking hold as the distant clouds grow larger in every window. Neptune's gravity pulls close to what you would feel standing on Earth, just slightly stronger, enough to make every movement inside the cabin feel a touch heavier than normal. A researcher who worked on the Voyager 2 mission once described arriving at Neptune as reaching the edge of the map. Beyond this point, for decades, human knowledge of the solar system simply ran out completely. You are now flying past that very edge. From here, Earth is not even a visible dot in your rear window, lost somewhere among countless other points of light. Everything familiar about home, its warmth, its blue skies, its oceans full of ordinary liquid water, belongs to a small, bright world nearly 3 billion miles behind you now. Out here, sunlight is a rumour more than a resource, and every system on your ship runs on stored power instead. The distance also means help is impossible to reach in time. A message sent back to Earth right now, travelling at the speed of light, would take over 4 hours just to arrive. Any signal calling for rescue would take another 4 hours to return after that. By the time anyone back home even knew you were in trouble, you would already know exactly how the story ends. There is no calling home from out here, no waiting for backup to arrive. Whatever happens next happens to you alone, 3 billion miles from anyone who could possibly help. A distant glow catches your attention through the front window, growing brighter and richer as your ship closes the remaining distance. The clouds ahead are not simply grey or white like the ones back home. They glow with a deep, saturated blue, rich enough to look painted onto the darkness of space itself. That colour has a story of its own, and it is about to explain itself before the real descent even begins. The blue is the first thing anyone ever notices about Neptune, and it is also the first thing that quietly fools them. From a distance, this planet looks almost gentle, a soft, glowing sapphire hanging in the dark. That colour comes from methane gas sitting in the upper atmosphere. Methane absorbs red light and reflects blue back out into space, the same basic idea behind why the ocean on Earth looks blue whenever sunlight strikes the water. But Neptune's blue runs deeper and richer than Uranus, its neighbour and near twin in overall size. Both planets contain methane, yet Neptune shows a darker, more vivid shade, and scientists are still studying exactly why the two worlds look so different, despite being built from strikingly similar ingredients. One idea points to a thin haze layer sitting high in Neptune's atmosphere, a mist that changes how sunlight scatters before it ever reaches an observer's eyes. Another idea suggests something deeper in the clouds is absorbing extra light before it can escape. Neither idea has been fully confirmed yet. For now, the true reason behind that deep, glowing blue remains an open question scientists have not fully answered. Photographs taken decades apart show that Neptune's colour even shifts slightly over time, brightening and dimming in patches that seem tied to the planet's slow, decades-long seasons. A world this far from the Sun should barely change at all from one telescope image to the next. Neptune keeps proving that assumption wrong, one quiet photograph at a time. Your ship drops lower, and the colour around the hull begins to shift. What looked like a smooth, painted sphere from a distance breaks apart into churning bands of cloud, moving at different speeds, colliding and twisting against each other in patterns too complex to track by eye. This is where the calm illusion ends completely. Sensors detect wind speeds building outside your hull, faster than anything ever recorded on Earth, fast enough to tear apart a commercial airplane within seconds. The soft blue marble from your approach has already become a violent, roaring sky stretched out in every direction. A planetary scientist once compared Neptune's atmosphere to a calm painting hiding a hurricane behind the frame. From orbit, you see only brushstrokes. Up close, you feel the actual storm underneath them. Your instruments pick up something new, a dark oval patch rotating just ahead of your flight path, vast enough to swallow a continent whole. It appears, disappears, and reshapes itself over the years, following rules scientists have not fully mapped out yet, even after decades of watching. This is not marked on any chart your ship carries. Neptune's weather changes faster than humans have been able to study closely, since telescopes only started watching this planet in real detail within the last few decades. The clouds ahead darken sharply, and your ship's collision sensors begin tracking the outer edge of something massive. Photographs sent home by telescopes make this planet look painted, still, and calm, the kind of image people print onto posters and hang on classroom walls. None of those pictures capture motion, sound, or force. None of them prepare a traveller for what waits on the other side of that peaceful-looking surface. The blue calm you saw from a distance was never the whole story. The real Neptune is waiting just past the clouds. The clouds swallow your ship whole, and the calm silence of open space disappears in an instant. Your first few seconds inside Neptune's atmosphere feel like driving straight into a wall of wind. The hull shakes violently as gas rushes past faster than anything a pilot back on Earth ever trains for. Warning lights flicker across your dashboard, then steady out as the ship's systems adjust to the new pressure pressing in from every direction. Outside your window, everything has gone a deep, hazy blue. Visibility drops to almost nothing beyond a short distance, since thick methane clouds scatter what little light reaches this far from the sun. You're flying blind through a fog thicker than anything ever recorded in an airplane back home. Your speed matters more than anything else right now. Enter too fast and friction against the thickening gas could burn through the hull before you ever reach a safer layer. Enter too slow, and Neptune's powerful gravity, close to what you would feel standing on Earth, pulls you downward regardless, forcing a descent no matter how carefully you try to control it. A flight engineer who designs atmospheric entry systems once compared this moment to skydiving through fog thick enough to hide a mountain range, with no way to know what shape the ground below might take, since Neptune has no ground at all. Sensors detect the outside temperature falling fast, dropping toward levels that would freeze exposed skin almost instantly. At the same time, friction against your hull generates intense heat on the outer plating, two extremes fighting each other only inches apart, separated by a wall of metal built to survive both. Inside the cabin, the temperature stays steady and controlled, a thin, artificial bubble of comfort surrounded by conditions that would end a human life in seconds. That bubble is the only reason you're still alive right now, and every alarm on the dashboard exists to warn you the moment it starts to fail. The ship rattles harder as it crosses into denser gas. What looked like a smooth, painted sphere from orbit has become a churning, turbulent sky, filled with invisible currents shifting speed and direction without warning. Your instruments begin picking up the first real readings of Neptune's wind, and the numbers climbing across your dashboard are already higher than anything measured on any storm in Earth's recorded history. This is only the outer atmosphere, the thinnest, calmest layer this planet has to offer. Deeper down, according to every model scientists have built, conditions only grow more violent, more crushing, and more strange. Your ship's automated log records every reading in silence, building a data trail nobody has ever collected before at this depth. Whatever happens next, that log becomes the closest thing to a first-hand account this planet has ever produced. A warning tone sounds steadily now, tracking wind speed as it climbs past what any aircraft on Earth could survive intact. You brace as the ship banks hard, catching the edge of a fast-moving current strong enough to spin a smaller craft completely off course. Neptune just gave you a preview of what everyone who studies this planet already knows. The wind here does not simply blow. It rages, faster than anywhere else in the entire solar system, and you're flying straight into the heart of it. The number climbing across your dashboard should not be possible. Wind speeds outside your hull are pushing past 1,200 miles an hour, faster than the speed of sound back on Earth, and faster than any storm ever measured on any planet in our solar system. Hurricane force winds on Earth start around 75 miles an hour. Neptune's fastest winds move more than 15 times stronger than that. To put that number somewhere you can actually feel it. Imagine the strongest hurricane ever recorded on Earth, then imagine 4 of them stacked directly on top of each other, blowing in the same direction at once. That combined force still would not fully match what is tearing past your ship's hull right now. This should not make sense. Neptune sits nearly 3 billion miles from the Sun, receiving barely any warmth at all, roughly 900 times weaker than what reaches Earth. Weak sunlight should mean a calm, sluggish atmosphere with little energy to power storms of any kind. Instead, Neptune hosts the fastest winds of any planet ever studied, born almost entirely from energy the planet generates on its own, deep inside layers your ship has not even reached yet. Scientists still debate the exact source of that hidden power, but whatever it is, it drives a wind system stronger than anything sunlight alone could ever create. A planetary scientist who studies extreme weather once compared Neptune's atmosphere to an engine running without an obvious fuel source, roaring at full power while the gauge that should explain where the energy comes from stays strangely empty. Your ship shudders as it crosses a fast-moving jet stream, gas moving at wildly different speeds only a short distance apart, twisting and shearing against itself the way 2 conveyor belts moving in opposite directions would tear apart anything caught between them. Outside, the temperature remains brutally cold, colder than anywhere on Earth has ever recorded, proving that speed and warmth do not need to travel together. Neptune manages to be both the coldest and one of the fastest moving worlds in the entire solar system at the same time. Pilots back on Earth train for turbulence measured in a handful of rough seconds before the sky calms again. Neptune offers no such calm stretch. The wind here does not gust and settle, it simply keeps blowing, hour after hour, year after year, across a planet with no mountains or coastlines anywhere to slow it down. Sensors track a massive band of clouds racing past below, moving so quickly that features large enough to be seen from Earth's most powerful telescopes shift position within a matter of hours. A gust catches your ship broadside, shaking the hull hard enough to rattle every loose panel inside the cabin. For a moment the ship tips dangerously off its planned path before stabilizers fight the wind back under control. Every simulation run back on Earth before launch predicted a rough ride through this outer layer. None of those simulations fully matched what the hull is registering right now. Real numbers, gathered live from inside an actual ice giant, are already rewriting assumptions engineers spent years building into the flight plan. This is only the beginning of Neptune's violence, a planet where speed and cold combine into something no world closer to the Sun has ever produced. Somewhere ahead, sensors detect a shape forming in the clouds, dark, massive, and growing larger by the second. Neptune's wind was only the warning. The storm itself is just coming into view. The shape ahead fills your entire view now, a dark oval patch larger than the whole planet Earth, spinning slowly against Neptune's glowing blue backdrop. Scientists first spotted a storm just like this one when Voyager 2 flew past Neptune in 1989, and they gave it a simple name: the Great Dark Spot. It looked permanent, a signature feature of the planet similar to Jupiter's famous red storm that has raged for centuries without stopping. Then something strange happened. When the Hubble Space Telescope looked at Neptune again just a few years later, the storm had completely vanished, as if it had never existed at all. No planet in the solar system had ever done that before. Jupiter's storm has spun for hundreds of years without pause. Neptune's storm appeared, raged with winds stronger than anything on Earth, and then disappeared within a matter of years. Scientists are still debating exactly why. One idea suggests the storm drifted toward the equator and broke apart under different wind patterns found there. Another idea points to deeper currents beneath the clouds pulling it apart from below, unseen and unmeasured. Nobody watched the exact moment it happened. Nobody knows for certain. A team of astronomers tracking Neptune later found new dark spots forming and vanishing in the years that followed, proving the first one was not a rare, one-time event. This planet builds and destroys storms bigger than entire worlds, over and over again, largely hidden from human eyes between rare telescope observations. Earth's own hurricanes weaken once they cross over land or cooler water, starved of the warm ocean fuel that built them in the first place. Neptune's storms have no coastline to cross and no cooler water waiting nearby. Whatever eventually kills one of these massive systems, it is not running out of fuel the way a storm back home would. Your ship's sensors show a new dark patch forming just ahead, smaller than the original storm but growing fast, feeding on the churning bands of gas swirling around it. Picture Neptune's atmosphere like a pot of water just before it boils, except the bubbles here are storms wider than continents, appearing and popping according to rules nobody has fully written down yet. You adjust course to avoid the spinning edge, but turbulence grows rougher by the second. Every warning light on your dashboard confirms what your instruments already suspected. This is not a calm, steady gas layer. It is an active, violent system, actively rebuilding itself while your ship flies straight through the middle of it. Something about that unpredictability should concern you more than the raw wind speed alone. If a storm the size of a planet can appear and disappear without warning, there is no way to fully know what might be forming directly in your flight path right now. Astronomers back on Earth rely on a handful of scheduled telescope sessions each year to track changes like these, brief windows of observations scattered across a planet that never stops moving. Most of what happens on Neptune between those windows happens completely unseen, hidden from every instrument humans have ever pointed toward it. Your ship pushes past the dark spot's outer edge, and the temperature gauge begins a drop unlike anything recorded since the descent began. Neptune has already shown you speed and violence. It is about to show you exactly how cold the outer solar system can truly get. The temperature reading outside your hull now sits far below anything a human being has ever experienced and lived to describe. Neptune's cloud tops drop to nearly 360 degrees below zero on the Fahrenheit scale. To put that number somewhere you can actually feel it, water freezes at 32 degrees. This cold runs more than 10 times colder than that freezing point in the opposite direction, a temperature extreme enough to turn ordinary materials brittle and strange. Steel, the metal used to build bridges and skyscrapers back on Earth, becomes fragile at temperatures this low. It can crack apart like glass under a hard enough impact. Rubber seals on an ordinary spacecraft would harden and snap within seconds. Fuel lines would freeze solid unless specially built to withstand conditions like these from the very start. Your human body would not last even a fraction of a second unprotected out there. Exposed skin would freeze almost instantly on contact with the outside air. Breathing would not even be possible, since oxygen makes up none of Neptune's atmosphere at all, not even a small trace of it. A researcher who studies the outer planets once compared Neptune's cold to the inside of a chest freezer, then quickly admitted that comparison badly undersells the truth. A chest freezer usually sits around 0 degrees Fahrenheit. Neptune runs over 300 degrees colder than that, a gap far larger than the entire distance between a warm room and the freezer itself. Yet this brutal cold only describes the cloud tops, the outermost thinnest layer of the whole planet. Your ship continues falling, and the pressure begins climbing in a way your instruments were never fully built to measure with confidence. Cold and pressure together create a strange effect down here. Gases that would normally stay gases back on Earth start behaving like liquids, then like solids, all without ever truly freezing in the traditional sense anyone on Earth would recognize. Your ship's hull groans under stress no design team back on Earth ever tested against directly. Every surface reading confirms the same brutal story, a planet locked in permanent, crushing cold from top to bottom. Antarctica holds the record for the coldest temperature ever measured on Earth, close to negative 130 degrees Fahrenheit during a rare winter night. Neptune's cloud tops sit more than 200 degrees colder than that record, a gap so wide that Antarctica would feel almost mild by comparison. A warm afternoon set against an endless, airless winter. Yet sensors detect something impossible deeper inside the planet. Heat, real heat, rising from somewhere far below, growing steadily stronger the deeper your instruments manage to read. That should not be possible on a world receiving almost no warmth at all from a sun sitting nearly 3 billion miles away. Something inside Neptune is generating its own energy, quietly and constantly, and whatever the true source turns out to be, it appears powerful enough to help drive the fastest winds in the entire solar system. Your ship's sensors lock onto that hidden heat signal, tracing it downward through the layers ahead, and the mystery only grows stranger the closer you get. Nothing in your training back on Earth covered a moment like this, watching one gauge report record breaking cold while another, only a short distance away on the same display, begins climbing toward heat nobody expected to find out here at all. Every planet should follow a simple rule. The heat it releases should roughly match the heat it receives from the sun. Neptune breaks that rule completely. Despite sitting nearly 3 billion miles from the sun, in the coldest, dimmest region of the entire solar system, Neptune radiates about 2.5 times more heat than it actually receives from sunlight. Somewhere deep inside this planet, something keeps generating its own energy, quietly and constantly, without any outside source to explain it. Scientists call this Neptune's internal heat problem, and decades after Voyager 2 first measured it, nobody has fully solved the mystery. One leading idea points to gravity itself. As Neptune slowly contracts under its own enormous weight, that gentle squeezing motion converts into heat, similar to how rubbing your hands together warms your palms through simple friction. Another idea suggests heavier materials slowly sinking toward the planet's center, releasing energy as they fall, like a stone dropping through water and warming slightly on its way down. A third idea is stranger still. Some researchers believe that deep inside Neptune, under pressure strong enough to reshape matter itself, carbon atoms are being squeezed so hard they form solid diamonds, which then sink toward the planet's core. That falling motion could release friction and heat along the way, like tiny stones falling through thick liquid and warming everything around them. Nobody has confirmed which explanation is correct. It remains one of the biggest open questions about this entire planet. Uranus, despite sharing a nearly identical size and makeup with Neptune, does not show this same extra heat in nearly as strong a form. Two planets built from almost the same ingredients, sitting in a similar cold, dark region of space, and only one of them runs its own hidden engine. Nobody has a full explanation for why the twins turned out so differently. Your ship's instruments pick up the heat signature growing stronger below, radiating upward through layers of compressed gas and liquid pressing in from every direction. Whatever the true cause turns out to be, that hidden energy source likely powers the extreme winds tearing through the atmosphere above you, winds faster than anywhere else in the solar system, born from heat that should not even exist this far from the sun. A planetary scientist once described Neptune as an engine running on fuel nobody has ever directly seen. It burns quietly, far beneath the visible surface, driving a storm system that dwarfs anything ever recorded on Earth. Your ship shudders as it crosses into a new layer, sensor readings shifting fast now. Pressure keeps climbing at a pace your instruments were never designed to track for long. Temperature outside remains brutally cold, yet somewhere below, that mysterious heat keeps growing stronger with every passing mile. If diamonds really are falling through this planet's middle layer, as some researchers suspect, your ship is now flying directly into the region where that process might actually be happening in real time. The pressure gauge spikes sharply again, and for the first time since the descent began, your outer sensors detect something solid moving through the compressed gas surrounding the hull. Whatever is falling through Neptune's middle layer, you're about to fly straight through the middle of it. Your outer sensors are no longer reading pure gas. Something is drifting past your ship now, small, dense, and catching the faint light in sharp, sudden flashes. Deep inside Neptune, roughly halfway between the cloud tops and the planet's distant core, pressure and heat reach levels almost impossible to picture clearly. Scientists suspect this middle layer, sometimes called the mantle, might hold conditions capable of turning ordinary gas into something completely unexpected. Researchers have long wondered whether this hidden layer could be the true source of Neptune's strange internal heat, its tilted magnetic field, and its unusually active weather. A region this deep, squeezed under crushing pressure and scorching heat, likely behaves unlike anything ever directly observed by human instruments. A geophysicist who studies planetary interiors once compared this middle layer to a locked room inside a house that nobody has ever been allowed to enter, one where scientists can only guess at the furniture based on sounds heard through the walls. Your ship's sensors track thousands of tiny fragments drifting past the hull, catching what little light remains at this depth and scattering it into brief, sharp glints across the cabin windows. Nobody built these instruments expecting to see solid material moving through what should still technically be a gas layer. That drifting motion may connect directly to the heat mystery uncovered earlier, the strange warmth rising from somewhere deep inside this planet despite its extreme distance from the sun. If dense material really is sinking slowly through these layers, friction and gravity could be converting that motion into energy, adding warmth to a system that should otherwise stay cold and quiet this far out. A planetary scientist who models Neptune's interior once explained it simply. Whatever process is happening down here does not need sunlight to keep running. It only needs enough pressure, enough heat, and enough time, all three of which this deep hidden layer has in abundance. No camera has ever captured an image of this region. No probe has ever sent back a single direct reading from inside it. Everything scientists believe about this layer comes from mathematics, laboratory experiments squeezed into tiny chambers, and careful comparisons with other worlds, pieced together like a puzzle missing most of its picture. Your ship pushes further into the thickening material, engines straining harder against resistance that behaves less like open sky and more like a dense shifting fog. Every reading confirms the same conclusion. You have left the atmosphere behind in the way anyone on Earth would normally understand that word. Ahead, your instruments detect the pressure spike again, sharper this time, as the middle layer begins shifting into something even stranger than before. Scientists have a theory about exactly what might be happening to ordinary gas molecules squeezed this hard, this deep, for this long. It involves carbon, immense pressure, and a transformation most people only ever picture inside a jewelry store window. Similar transformations happen on Earth too, though on a vastly smaller and gentler scale. Natural diamonds mined from deep underground, formed under intense heat and pressure over long stretches of time, buried far beneath the surface long before anyone dug them free. Neptune runs that same basic process constantly, at a scale no mine on Earth could ever come close to matching. The layer ahead may be manufacturing something far stranger than gas, quietly, constantly and completely by accident. Your ship's collision sensors chime softly, tracking dozens of small, dense objects drifting steadily downward all around the hull. Methane is built from carbon and hydrogen bonded tightly together. Crush that bond hard enough, heat it high enough, and the connection finally breaks apart. Scientists estimate the pressure inside Neptune's middle layer climbs past 1 million times what you feel standing on Earth's surface, under conditions that extreme methane gas cannot hold its normal shape. The hydrogen atoms drift away first, light and quick to escape. The carbon atoms left behind get squeezed so tightly they lock into the exact same crystal structure found inside a diamond ring. This is not a theory pulled from pure imagination. Researchers have recreated similar conditions inside laboratories on Earth, using powerful lasers to compress small samples of material for a tiny fraction of a second, and tiny diamonds formed exactly as scientists predicted they would. Picture the difference between a lump of coal and a polished diamond. Both are built from the same element, carbon. The only real difference between them is how tightly that carbon gets squeezed together. Neptune's middle layer works like a machine built for exactly that kind of squeezing, on a scale far larger than anything humans could ever construct. Your ship's sensors track the crystal fragments drifting steadily past the hull, denser than the slushy material surrounding them, pulled downward by gravity in a slow, constant drift that scientists studying this process have started calling diamond rain. A geophysicist who studies planetary interiors once compared this to snow falling in reverse, glittering material sinking down instead of drifting up, heading toward a destination it can never truly reach, since Neptune has no solid surface anywhere for it to land on. That constant downward drift may explain part of the deeper mystery uncovered earlier, the strange heat rising from somewhere far below. As dense diamond crystals fall through the layers beneath your ship, friction and gravity convert their motion into warmth, feeding energy into a system that should otherwise stay cold and still this far from the sun. Estimates suggest some of these crystals could grow to sizes far beyond anything ever cut and polished back on Earth, massive compared to any stone ever pulled from a mine, drifting endlessly through crushing pressure and total darkness. The largest diamond ever found on Earth weighed a little over 1.25 pounds before it was cut down for display. Researchers studying Neptune's interior suspect some crystals forming down here could dwarf that record many times over, an entire hidden treasury with no vault, no owner, and no way for anyone to ever collect a single piece of it. A chemist who studies extreme pressure environments once said the strangest part is not that diamonds might exist down here, it is that nobody will ever collect a single one, since retrieving anything from this depth would require surviving pressure that has crushed every previous idea engineers have proposed. Your ship tracks the largest fragments on radar, glinting briefly before vanishing back into the dark material surrounding them. Down here, wealth beyond ordinary imagination drifts endlessly through darkness, belonging to no one, going nowhere, falling toward a core it may never actually reach. Ahead, your instruments detect a much larger shift in the readings. The diamonds are not simply falling into empty space anymore, they are falling into an ocean. An ocean should not exist this deep inside a planet, under this much pressure, at temperatures this extreme. Yet that is exactly what your instruments are detecting now, a vast layer of liquid stretching for thousands of miles beneath Neptune's clouds, made from a superheated mixture of water, ammonia and methane, all crushed together under pressure strong enough to reshape ordinary chemistry itself. Scientists call this a supersonic ocean, and it behaves nothing like the water sitting in any ocean back on Earth. On Earth, water molecules stay bonded together as they move, flowing and splashing as one connected substance. Inside Neptune, the pressure is so extreme that those molecules start breaking apart completely. Oxygen atoms form a loose shifting structure, almost like an invisible cage, while hydrogen atoms move freely through it, carrying electric charge with them as they travel. That constantly moving charge turns this strange ocean into a powerful conductor of electricity, similar to how the copper wiring inside your home conducts an electric current, except stretched across a scale thousands of miles wide, buried far beneath crushing layers of pressure. Researchers believe this electrically charged ocean is the true source of Neptune's tilted, unusually shaped magnetic field, a signal first detected from Earth decades ago that never quite matched normal planetary behaviour. The ocean itself may act like a giant off-centre generator, humming with energy far beneath the visible clouds above. Temperatures inside this ocean reach several thousand degrees, hot enough to melt steel almost instantly. Yet the water does not boil away into steam, because the pressure pressing down from above is simply too strong to allow that change to happen. Heat and pressure fight against each other constantly down here, locked in a permanent standoff that creates conditions found nowhere else in the solar system. Laboratories on Earth have managed to recreate small pockets of this supersonic state for only brief moments, using powerful lasers to compress tiny water samples for a fraction of a second before the equipment reaches its own limits. Neptune runs this same extreme chemistry constantly, across an ocean thousands of miles wide, without any machine to switch it off. A planetary chemist who studies extreme environments once compared this ocean to water, trapped inside a sealed pressure cooker turned up impossibly high, unable to boil, unable to freeze, forced instead into a strange in-between state that barely resembles liquid water at all. Your ship's hull creaks under mounting stress as it crosses into the outer edge of this layer. Diamond fragments from the region above continue drifting downward, vanishing quietly into the dark liquid stretching endlessly in every direction around the hull. There is no bottom visible on any sensor reading, no shoreline anywhere nearby, no surface to aim for, just an ocean without end, wrapped entirely around the denser, hotter core hidden somewhere far beneath it. No submarine ever built on Earth could survive conditions like these for more than a few seconds. No spacecraft either, not without protection far beyond anything currently available to engineers. Your ship was built to survive extreme pressure, but nothing on Earth ever prepared its designers for numbers this large. The hull pressure alarm begins flashing steadily across your dashboard, and for the first time since the descent began, structural readings start climbing into genuinely dangerous territory. The alarm on your dashboard is not exaggerating anything. Your ship is now entering pressure that no human-made object has ever been tested against directly. At Earth's ocean surface, you feel about 14 pounds of pressure pressing against every square inch of your body, spread so evenly you never even notice it during an ordinary day. Dive to the deepest known point in Earth's oceans, the Mariana Trench, nearly 7 miles down, and that pressure climbs to over 16,000 pounds per square inch, strong enough to crush most submarines built for shallower depths. Neptune's ocean layer makes even that extreme number look small by comparison. Estimates place the pressure here at several million pounds per square inch, over 100 times stronger than the deepest point in any ocean on Earth. No steel hull, no matter how thick it is built, could hold its shape against force that extreme for very long. Metal does not simply shatter under pressure like this. It flows instead, bending and compressing slowly like soft clay before finally collapsing inward completely. A structural engineer who designs deep-sea submersibles once compared surviving Neptune's ocean layer to holding an eggshell together while standing directly underneath a loaded freight train. No amount of extra steel solves a problem at this scale. The physics simply does not allow for a simple fix. Every previous spacecraft humans have ever built, going back to the earliest missions launched decades ago, was designed for the near vacuum of open space, not for an environment actively trying to crush it into a smaller and smaller shape. Voyager 2, the only spacecraft to ever study Neptune up close, never came anywhere near this kind of depth. It skimmed past the outer clouds and continued onward into deep space, its instruments never built to withstand conditions like these. Even the probe's engineers once dropped into Jupiter, a planet with its own extreme pressure layers, only lasted a short while before losing contact, crushed long before reaching anything close to a solid layer. Neptune's ocean sits under even greater pressure than the depths that silenced those earlier probes. Your ship's outer plating groans again, sharper this time, and a warning light shifts from steady yellow to flashing red across the dashboard. Engineers back on Earth theorize that surviving even a short trip into this layer would require materials that barely exist yet. Dense metal alloys layered together with materials designed to spread pressure evenly across the entire hull, similar to how a car's crumple zone spreads out the force of a crash instead of absorbing it all in a single spot. None of that technology has ever been fully built. None of it has ever been tested against pressure this extreme, because nothing occurring naturally on Earth reaches numbers anywhere close to these. You're flying a ship built using today's best available engineering directly into a layer that punishes even the strongest materials science has ever created. Every material sample ever tested in a laboratory pressure chamber on Earth has a documented breaking point, a specific number where it finally gives way. Somewhere in the last few minutes, your ship's outer hull likely crossed past every one of those documented numbers, entering territory no test chamber back home was ever built large enough or strong enough to simulate. The hull begins vibrating at a frequency your sensors have never recorded before, and for the first time since launch, your instruments start calculating exactly how many seconds of structural integrity remain. That number is not large, and it is about to grow even smaller. The countdown on your dashboard is no longer measuring distance. It is measuring how long a human body could possibly survive if anything went wrong right now. The honest answer is almost nothing at all. At this depth, Neptune's atmosphere has already crossed from gas into something closer to liquid, without ever forming a clear line between the two states. There is no clean surface down here, no single moment where sky quietly becomes ocean the way it does back on Earth. Pressure and heat simply build, layer after layer, until gas behaves like liquid long before anyone could ever mark the exact boundary between them. For an unprotected human, exposure would end almost instantly. The extreme cold higher up in the atmosphere would already be enough to freeze exposed skin within seconds. Down here, the danger shifts completely. Crushing pressure would collapse the human chest before the lungs even finish drawing a single breath, and there is no oxygen anywhere in this atmosphere to breathe in the first place. A flight physiologist who studies extreme environments for space agencies once explained it simply. The human body evolved to survive within a narrow, gentle range of pressure and temperature, roughly matching conditions found within a few miles of Earth's own ocean surface. Neptune's middle layers exceed that safe range by numbers so large the comparison barely makes sense anymore. Even trained deep-sea divers, wrapped in specialized suits built to handle extreme pressure, stay limited to a small fraction of what your hull is pushing through right now. Every safety record humans have ever set underwater on Earth would be shattered many times over before your ship even reaches the ocean layer waiting below. Your ship remains sealed, its systems fighting to hold their shape against forces climbing higher with every passing second. Sensors show the outer hull temperature rising sharply now, not from the extreme cold outside, but from friction, as your ship pushes deeper against thickening material that resists movement more like syrup than open air. This is the layer scientists believe holds Neptune's superionic ocean, the electrically charged, crushed-together mixture of water, ammonia, and methane responsible for the planet's strange tilted magnetic field. Your ship is no longer flying through anything resembling open space. It is pushing through a substance that fights back with every single mile gained. Warning systems flash a new alert across the cabin. Structural stress has crossed into territory the engineers back on Earth marked as the outer limit of survivability for this entire hull design. There is no ejecting here, no parachute waiting to deploy, no rescue ship stationed nearby, no surface to land on even if you somehow slowed the descent in time. Neptune offers nothing solid to aim for, only deeper, denser layers stacking endlessly toward a core still thousands of miles below your current position. A researcher who modelled Neptune's interior once said, "Any spacecraft entering this deep should expect only one outcome, since nothing built by humans has ever been designed to stop safely once it starts falling into a layer like this one. Your ship's systems begin recalculating survival estimates in real time, and the numbers keep shrinking with every second that passes. For now, your hull is holding. But holding steady is not the same thing as being safe, and the descent has not finished revealing what still lies below. While your ship fights to hold together against crushing pressure, something high above you keeps spinning at a pace that barely gives Neptune a moment to rest. A full day on Neptune, one complete spin of the entire planet, lasts about 16 hours. That is faster than a full day on Earth, even though Neptune itself measures nearly 4 times wider than our planet. Picture something the size of a school bus spinning in place, faster than something the size of a small car parked right next to it. The larger scale should slow the spin down. Instead, Neptune manages to turn even quicker than home. That fast rotation reshapes the entire structure of the planet. Neptune is not a perfect sphere. Like a ball of soft clay spun rapidly on a table, the planet bulges slightly wider at its middle and flattens slightly at its poles, a shape scientists call an oblate spheroid. Your ship's sensors confirm that distortion directly, tracking a measurable difference between Neptune's width at the equator and its height from pole to pole, a gap that would be completely invisible on a slower spinning world like Earth. This fast spin also feeds directly into the extreme winds tearing through the atmosphere above you. As gas near the equator moves faster than gas closer to the poles, that difference creates powerful shearing forces, similar to 2 conveyor belts running at different speeds right next to each other, dragging and twisting apart anything caught in between them. A planetary scientist who studies rotating gas worlds once compared Neptune's spin to a figure skater pulling their arms in tight, moving faster and faster the more compact their shape becomes. Neptune formed compact and fast from the very beginning of the solar system, and billions of years later, it still has not slowed down in any meaningful way. 16 hours might sound short, almost convenient, until you remember exactly what that spin is dragging along with it every time it turns. Storms wider than Earth itself, winds faster than anywhere else in the solar system, and a churning, layered atmosphere with no solid ground anywhere to slow any of it down through simple friction. On Earth, mountains, oceans, and stretches of land create drag that gradually calms storm systems over time. Neptune has none of that available, just endless layers of gas and liquid spinning fast with almost nothing anywhere to interrupt the motion. Different bands of Neptune's atmosphere actually rotate at slightly different speeds from each other, a phenomenon scientists call differential rotation, similar to lanes of traffic moving at different speeds on the same highway. That mismatch alone helps generate some of the powerful shearing winds tearing past your hull right now. Your ship's navigation system struggles briefly to lock onto a stable reference point since the entire planet beneath you is rotating faster than most spacecraft systems were ever designed to track this close to the surface. Astronomers actually measure Neptune's exact rotation speed by tracking its magnetic field rather than watching cloud patterns directly, since the clouds themselves shift and drift too quickly to give a reliable reading on their own. The magnetic field generated deep inside the planet offers a steadier clock buried far beneath all that surface chaos. That fast spin explains the short days perfectly well. It does nothing to explain the years. Because while Neptune finishes a full spin in under 17 hours, completing a single trip around the Sun takes this planet far longer than any human being has ever lived to witness. Every birthday you have ever celebrated marks one full trip around the Sun. On Neptune, nobody has ever lived long enough to celebrate even a single one. A full year on Neptune lasts about 165 Earth years. To put that into a picture you can actually hold on to, if a spacecraft launched from Earth on the exact day Neptune was first discovered, it still would not have completed one full Neptune year by today. Neptune was actually discovered in 1846. That means this planet has only finished a single complete orbit around the Sun since human beings first confirmed it existed at all. Distance explains most of that difference. Neptune orbits nearly 3 billion miles from the Sun, far outside Earth's own orbit, and the Sun's gravity pulls far more weakly out at that range. Weaker gravity means Neptune moves through space much slower than Earth does, stretching a single lap around the Sun into a journey longer than any human lifetime could ever cover. Your ship's navigation system flags something unusual as it calculates Neptune's orbital path, a strange, distant relationship with a much smaller world nearby. Neptune's gravity is powerful enough to influence the orbit of Pluto, locking the two worlds into a steady rhythm where Pluto circles the Sun twice for every 3 times Neptune completes the same journey, a pattern astronomers call orbital resonance. That relationship has held steady for longer than human civilization has existed. Two worlds separated by enormous distance, still gravitationally tied together like dancers following the same slow, repeating pattern for millions of years without ever missing a step. Every human year measured since Neptune's discovery represents only a small sliver of a single lap this planet takes around the Sun. Entire empires have risen and fallen, wars have started and ended, and generations of families have lived complete lives. All within a stretch of time, Neptune still counts as a single unfinished year. A planetary scientist who studies orbital mechanics once compared Neptune's year to a marathon so long that no single runner could ever finish it alone. Generations would need to pass the same finish line forward, over and over, before the race was ever truly complete. Your ship continues its descent, and the numbers on the dashboard feel increasingly abstract. Orbital calculations, pressure readings, temperature extremes, none of it matching anything a human mind evolved to process comfortably or quickly. This slow orbit also connects directly to something else about Neptune, something that shapes the entire experience of existing, in theory, anywhere on this world. A year this long stretches far beyond a longer calendar hanging on some distant wall. It means the seasons themselves stretch out into lengths that barely make sense to a species built around a single, fast lap around a much closer, warmer Sun. Your ship's sensors detect subtle shifts in cloud patterns far above the hull, tied to Neptune's slow seasonal cycle, changes that unfold gradually over decades rather than months or weeks. Down here, sealed inside a ship fighting crushing pressure, the idea of a single season lasting longer than an entire human life feels less like an abstract fact and more like a quiet warning about just how different this whole world truly is. Imagine a single season, just one, lasting longer than your entire childhood, your entire career, and most of your retirement combined into one stretch of time. That is what a season looks like on Neptune. Since a full year on this planet lasts about 165 Earth years, each individual season, spring, summer, fall and winter, stretches out to roughly 40 years long. A person could be born, grow old, and pass away without ever once seeing Neptune complete a single, full-season change from start to finish. Your ship's sensors track faint shifts in cloud brightness near Neptune's southern regions, patterns astronomers back on Earth have been quietly recording for decades. Telescopes have watched this planet slowly brightening in certain areas over the years, a subtle clue suggesting Neptune South is currently experiencing summer, a season that began long before many people currently alive were even born. A team of astronomers using the Hubble Space Telescope confirmed these long-term brightness changes by comparing images taken years apart, results that would be completely invisible within a single night of observation. Only by watching patiently, year after year, did the true pattern slowly reveal itself. This slow pace connects directly to Neptune's steep axial tilt, similar in basic concept to how Earth's own tilt creates our 4 seasons, except stretched across a distance and timescale that barely fits inside normal human understanding. As Neptune slowly circles the Sun, different regions spend decades tilted toward what little sunlight reaches this far out, then decades more tilted away from it completely. A planetary scientist who studies long-term climate change on gas worlds once compared Neptune's seasons to watching a clock with a single hand so slow that an entire human lifetime might pass while the hand barely appears to move at all. Astronomers only began seriously tracking these seasonal changes within the last few decades, meaning nobody on Earth has ever watched Neptune complete even 1/4 of a single season from start to finish. Everything scientists currently know about how these seasons behave comes from a small slice of a much longer, still unfinished pattern. Your ship continues its descent through layers that seem completely indifferent to time itself. A planet where a season change measured in decades feels almost meaningless compared to the raw physics happening beneath the clouds right now, in this exact moment. Yet these slow seasonal shifts likely still influence the storms above you, subtly changing wind patterns and cloud formation across the span of decades, adding one more layer of complexity to a planet already breaking nearly every rule Earth ever trained you to expect from a world. Future generations of scientists, people not yet born, will inherit the task of finishing this seasonal picture, watching Neptune's south fade from summer into fall over the coming decades, while researchers today can only lay the groundwork for observations they may never personally see completed. Your dashboard flashes a new alert, pulling attention away from slow-moving seasons and back towards something far more immediate. Structural readings continue climbing steadily, and your ship's systems begin cross-referencing historical mission data, searching for any previous flight that faced conditions anything like these. The search returns almost nothing useful. Only one spacecraft in human history ever came close enough to study this planet directly, and even that mission never attempted anything close to what your ship is doing right now. Before any spacecraft ever photographed Neptune, before any telescope ever confirmed it existed, this planet was already predicted, on paper, through pure mathematics alone. In the early 1800s, astronomers studying Uranus noticed something strange. Its orbit around the Sun did not perfectly match the calculations predicted by gravity alone. Something invisible seemed to be tugging on it steadily, pulling it slightly off its expected course. Two mathematicians working independently in different countries used those small orbital irregularities to calculate roughly where an unseen planet must be hiding in the dark. Urbain Le Verrier in France and John Couch Adams in England both reached similar conclusions using nothing more than pencil, paper, and Newton's laws of gravity. In 1846, an astronomer pointed a telescope toward the exact patch of sky Le Verrier had calculated, and found Neptune within a single night of searching. A planet nearly 3 billion miles away, discovered not by simply looking up at random, but by mathematics predicting exactly where to look before anyone ever saw it directly with their own eyes. Few discoveries in the history of science have ever worked quite that way. Your ship's onboard systems briefly display a historical file, a small tribute added by engineers back on Earth, marking the spot where mathematics first proved a planet could exist before human eyes ever confirmed it firsthand. That discovery reshaped how scientists understood the entire solar system, revealing a boundary far larger than anyone had previously believed, and setting the stage for later questions about what else might still be hiding in the dark beyond it. A dispute over credit followed the discovery for years afterward, since both Le Verrier and Adams had independently reached similar answers before the planet was actually found through a telescope. Astronomers eventually agreed to honour both mathematicians for their work, a rare case in science where two separate minds solved the same distant puzzle almost at the same time, without ever speaking to each other. For over a century after that first discovery, Neptune remained almost entirely a mystery, a distant point of light even in the most powerful telescopes on Earth, its clouds, storms and moons completely invisible to human eyes for generation after generation. That changed only once, in 1989, when Voyager 2 became the only spacecraft in human history to fly close enough to study Neptune directly. A scientist involved with that historic flyby once described the encounter as humanity's only real glimpse of Neptune up close, a single visit lasting only hours after a journey that took over a decade to complete from launch to arrival. Your ship's systems compare that single historic flyby to the mission happening right now, and the difference could not be more extreme. Voyager 2 skimmed past the outer clouds and continued onward into deep space. It never came close to this pressure, this depth, or this level of danger. You're already far beyond anywhere that spacecraft ever travelled in its brief encounter with this planet. The dashboard flashes again, sharper this time. Structural warnings climbing into territory no engineer back on Earth ever expected a spacecraft to survive for long. Neptune took mathematics to discover from a distance. Surviving it up close may take something science has not fully figured out yet. Deep inside your ship, a sensor built to track magnetic fields starts behaving strangely, spinning through readings that refuse to settle into a normal pattern. Every planet with a strong magnetic field usually keeps that field lined up close to its spin, the way a compass needle back on Earth points roughly toward the true North Pole. Neptune breaks that pattern completely. Its magnetic field tilts about 47 degrees away from the planet's spin, a lean so extreme that nothing comparable exists anywhere else among the 8 planets. The field sits offset from the planet's centre too, shifted far enough that some regions of Neptune experience a magnetic pull stronger than others, depending on where they happen to sit relative to that hidden crooked source. Scientists tie this strange shape directly to the electrically charged ocean layer your ship pushed through only a short while ago, the crushed-together mixture of water, ammonia and methane that behaves more like a shifting, moving generator than a calm body of liquid. Unlike Earth, where a solid, steady core produces a clean, centered field, Neptune's field seems to come from somewhere shallower and messier, closer to the surface, sloshing and shifting as the planet spins. A physicist who studies planetary magnetism once compared Earth's magnetic field to a single, steady flashlight beam pointed straight down a hallway. Neptune's field behaves more like a flashlight held by someone spinning in place, sweeping wildly across the walls instead of holding one steady direction. That wild, sweeping field creates something Earth has never produced. On our planet, auroras stay locked near the poles, glowing curtains of light triggered when charged particles funnel down along a steady magnetic path. Neptune's tilted off-center field spreads that glow across a much wider stretch of the planet, producing auroras that shift position constantly as Neptune spins through its short 16-hour day. Voyager 2 caught only a brief glimpse of this behavior during its single flyby, close enough to measure the tilt directly but nowhere near long enough to fully map how the pattern shifts over time. Everything scientists know about Neptune's auroras still comes from that one short visit decades ago, stitched together with careful guesswork. Your ship's sensors flicker again, caught in the pull of a field that refuses to behave the way training back on Earth predicted. Navigation systems built around steady, predictable magnetic readings struggle to lock onto a stable heading, forced instead to recalculate constantly against a field that never sits still. Whatever secrets are hidden in that tilted, wandering field, no instrument has ever spent enough time this deep to fully solve them. Every reading your ship collects right now writes new information into a story that has stayed unfinished since the day Voyager 2 flew past and kept going. Scientists studying the data have also noticed that the field strength varies noticeably from place to place across the planet, stronger in some regions and noticeably weaker in others, another sign that whatever generates it sits closer to the surface than a deep, stable core would allow. That brief flyby, decades ago, is still the only real visit this planet has ever received, and it left behind far more questions than answers. Voyager 2 remains the only spacecraft in human history to ever fly past Neptune directly, and everything it captured during that single encounter still shapes almost everything scientists understand about this planet today. The spacecraft launched from Earth in 1977, riding a rare alignment of the outer planets that let it swing past Jupiter, Saturn, and Uranus before finally reaching Neptune in 1989, 12 years after leaving home. That kind of alignment, allowing one spacecraft to visit 4 planets in a single mission, happens only once every couple centuries. During its closest approach, Voyager 2 passed within a few thousand miles of Neptune's North Pole, closer to this planet than any spacecraft has ever come before or since. In that brief window, it measured the record-breaking winds tearing through the atmosphere, spotted the great dark spot for the first time, and confirmed the planet's strange tilted magnetic field. The spacecraft also discovered several small moons circling Neptune that no telescope on Earth had ever detected, faint and hidden against the planet's glare. It captured the first close images of Triton, Neptune's largest moon, revealing dark streaks across its icy surface that scientists later identified as active plumes erupting from beneath the frozen ground. A member of the mission team once described watching Voyager 2's images arrive back on Earth as opening a door that had stayed locked for the entire history of human astronomy. Nobody had ever seen this planet up close before, and nobody has managed to see it that closely since. Voyager 2 also confirmed Neptune has rings, faint and dusty, nothing like the bright, easily visible rings circling Saturn. Ground-based telescopes had caught hints of something there years earlier, brief flickers as background stars passed behind the planet, but nobody could confirm exactly what those flickers meant until Voyager 2 flew close enough to see for certain. After collecting all of this in a matter of hours, the spacecraft continued moving, carried forward by the same momentum that had carried it across the solar system for over a decade. It never slowed down, never turned back, and never returned. Today it continues travelling through interstellar space, farther from home than any human-made object has ever travelled, still sending back faint signals from a distance that grows larger every single day. Your ship's systems compare its own readings against the old Voyager 2 data, decades old now, gathered during a visit that lasted only a matter of hours before continuing on forever. Everything humanity has learned about Neptune beyond that single flyby comes from telescopes millions of miles away, squinting at a tiny, dim planet near the edge of what any instrument on Earth can clearly resolve. Modern telescopes, including ones far more powerful than anything available in 1989, have helped fill in some gaps since then, tracking storms, measuring brightness changes, and confirming Neptune's slow seasonal shifts from a safe distance. None of them can match the detail a spacecraft flying directly past the planet once captured in a single afternoon. No mission has ever gone back for a longer look, and the reason why involves more than simple curiosity. Engineers who worked on the original Voyager mission never expected it to still matter decades later as the single best source of Neptune data available. Most of them assumed a follow-up mission would arrive within a couple decades, carrying better instruments and a longer, more detailed stay. That follow-up never came. Nearly 40 years have passed since Voyager 2's brief flyby, and in all that time no spacecraft has ever returned to Neptune. The reason starts with distance. A journey to Neptune takes over a decade using current propulsion technology, even when a spacecraft catches a helpful gravity assist from a planet like Jupiter along the way. Missions to Mars take months. A mission to Neptune demands patience measured in years before a single useful picture ever reaches Earth. Distance also creates a power problem. Solar panels work well close to the Sun, where sunlight arrives strong and steady. Out at Neptune, sunlight has already faded to a small fraction of its strength near Earth, far too weak to power a spacecraft's instruments and cameras. Missions this far out instead rely on small nuclear generators, devices that convert heat from radioactive decay into electricity, technology that is expensive, tightly regulated, and available in only limited supply. A mission planner who works on outer planet proposals once compared building a Neptune mission to planning an expedition to a mountain nobody has climbed in decades, where every single supply must be carried from the very first step, since no resupply of any kind will ever be possible once the journey begins. Budgets add another obstacle. Space agencies can only fund a limited number of major missions at any given time, and destinations like Mars, the Moon, and Jupiter's icy moons have historically been ranked as higher priorities, both for scientific interest and realistic cost. Neptune, distant and expensive to reach, has repeatedly lost out in that competition for funding. Scientists have proposed several serious missions to return to Neptune over the years, including detailed concepts for an orbiter that would circle the planet for an extended stay, paired with a smaller probe designed to drop directly into the atmosphere. None of these proposals has yet received full funding and a confirmed launch date, though interest among researchers has grown stronger in recent years as the gap since Voyager 2's visit continues to widen. Part of that growing urgency comes from timing. Certain planetary alignments make the journey to Neptune faster and more fuel efficient, and those alignments only occur during specific launch windows spaced years apart. Missing one window can add years, sometimes decades, onto the wait for the next realistic opportunity. Public interest has grown alongside that scientific pressure too, fueled partly by stunning reprocessed images of Voyager 2's original flyby, shared and reshared decades after they were first captured, reminding a new generation that this strange, distant planet still has far more to reveal. Your ship's onboard files include mission proposals dating back years, blueprints and plans that never made it past the drawing board, abandoned before a single piece of hardware was ever built. For now, everything scientists understand about this planet still traces back to a handful of hours in 1989, stretched thin across decades of careful, patient study from a distance. A closer visit remains possible. It would just require solving nearly every engineering problem your ship is currently fighting through in real time. Some scientists worry that waiting too long carries its own cost. The longer humanity goes without a real return visit, the more Neptune's slow seasonal changes drift outside anyone's ability to properly track and compare against the small window Voyager 2 once captured. If humanity ever sends another spacecraft to Neptune, engineers already know the mission will demand solving problems no previous outer planet mission has ever fully faced. A probe attempting real atmospheric entry, rather than a simple flyby like Voyager 2, would need to survive forces far beyond anything tested on missions to Mars or the Moon. Entry speeds at Neptune reach tens of thousands of miles an hour, fast enough that friction against the thickening atmosphere generates heat close to the surface temperature of a star, all within the first few minutes of arrival. The closest comparison humans have ever built came from a mission to Jupiter decades ago, when engineers dropped a small probe directly into that planet's crushing atmosphere. That probe survived under an hour before pressure and heat destroyed it completely, but not before transmitting a flood of valuable data back to a parent spacecraft waiting safely in orbit above. A propulsion engineer who worked on outer planet missions once explained that surviving entry is really a battle against a single brutal number: the speed at first contact with the atmosphere. Slow that speed down even slightly through careful trajectory planning and survival time stretches. Get the angle wrong, even by a small amount, and the whole mission ends in the first few seconds. Communication adds another layer of difficulty entirely. Signals travelling between Neptune and Earth take over 4 hours to cross that vast distance, meaning no team back home could ever guide a probe through its final descent in real time. Every command has to be pre-programmed months in advance, trusting a computer millions of miles from any human hand to make split-second decisions completely alone. Your ship carries systems built around exactly that kind of independence, running through emergency protocols without waiting for permission from anyone. Every alarm flashing across your dashboard right now gets answered by the ship itself, since no message calling for help could possibly arrive in time to matter. A future probe would also need shielding capable of surviving pressure that grows more extreme with every passing mile, the same crushing force currently testing your ship's hull to its absolute limit. Engineers studying this problem have looked at deep-sea submersible designs on Earth for inspiration, borrowing ideas from vehicles built to survive the deepest trenches in our own oceans, then scaling those ideas up to handle pressure far beyond anything found in any ocean on Earth. None of that shielding solves the heat problem waiting just outside the hull during entry, a separate challenge requiring an entirely different kind of protection, built to survive only the first few violent minutes before burning away completely. Engineers working on early Neptune mission concepts have already started testing scaled-down versions of these ideas in laboratory pressure chambers, pushing materials to their absolute limits long before any real spacecraft ever leaves Earth. Every successful test brings a real mission slightly closer to becoming possible. That protective layer has a name, and building one strong enough for Neptune remains one of the hardest unsolved problems in modern spacecraft design. Engineers cannot simply reuse the exact design that once protected the Jupiter probe either. Neptune's atmosphere carries a different mix of gases, moving at different speeds, striking a shield at a different angle and force than anything tested before. Every new destination in the solar system demands its own version of this same, extremely difficult problem, solved almost entirely from scratch. Before any spacecraft can survive Neptune's crushing depths, it first has to survive getting there, and that first challenge might be the hardest one of all. Entry speeds at Neptune push a spacecraft to tens of thousands of miles an hour before it even reaches the thickest part of the atmosphere. Friction against gas at that speed generates heat closer to the surface of the Sun than anything a spacecraft normally experiences, all concentrated onto a single point at the front of the vehicle within just a few short minutes. Engineers solve this problem using a heat shield, a thick sacrificial layer built to burn away on purpose, carrying dangerous heat with it as it disappears. The most extreme version of this technology ever built protected a small probe during its plunge into Jupiter decades ago, a mission that remains the closest comparison scientists have for what a Neptune probe would need to survive. That Jupiter probe lost roughly half its total heat shield mass during entry, an entire layer of protective material stripped away and carried off as glowing, superheated gas within a matter of minutes. Losing that much material on purpose, in a controlled way, was the entire point. Every ounce that burned away was heat that never reached the sensitive equipment tucked safely inside. A materials engineer who designs heat shields once compared the process to holding an ice cube inside a closed fist while walking briskly across hot coals. The ice slowly melts and steams away, but as long as enough of it remains by the final step, the hand underneath stays protected the entire way through. Neptune's atmosphere is thinner overall than Jupiter's, which slightly reduces the entry heat compared to that earlier mission, but the extreme entry speed still demands a heat shield built from some of the most advanced ablative materials engineers have ever developed. Every added inch of protective material also adds weight, and every added pound makes the spacecraft harder and more expensive to launch across billions of miles of empty space in the first place. That trade-off sits at the centre of every mission proposal scientists have drafted for a future Neptune probe, balancing just enough shielding to survive entry against a spacecraft still light enough to actually reach the planet in a reasonable amount of time. Some engineers have proposed a completely different approach, slowing a probe down using the atmosphere itself in careful, controlled stages, rather than relying entirely on a single, massive shield. That method could reduce how much protective material a spacecraft needs to carry, though it demands far more precise navigation than any previous outer planet mission has ever required. Your ship's outer hull carries scorch marks from its own violent entry, a visible record of exactly how much material burned away just to get this far. Whatever protective layer remains is likely thinner now than when this journey first began, worn down mile after mile by heat and pressure working together. No engineer back on Earth has ever built a shield tested against everything your ship has already survived, and the ship is still falling, deeper now than any heat shield in history has ever been asked to protect. Somewhere below, the light outside your window has already started changing in a way no camera has ever fully captured. Look outside your window right now, and the light has already changed completely from anything you saw during the earliest moments of this descent. Near the cloud tops, faint sunlight still managed to reach this far, weak and thin, but enough to paint the clouds in that deep glowing blue everyone recognizes from photographs taken back on Earth. That light travelled nearly 3 billion miles just to arrive here, stretched thin across a distance so vast it barely counts as daylight anymore by the time it lands. The deeper your ship falls, the faster that light disappears completely. Thick layers of gas and haze absorb what little sunlight remains, swallowing it mile after mile until almost nothing gets through at all. Within a relatively short distance below the visible clouds, true darkness takes over entirely, a blackness deeper and more complete than the darkest night ever experienced on Earth. A planetary scientist who studies deep atmospheres once compared this transition to walking from a sunlit beach into a cave, except the cave here stretches for thousands of miles straight down, with no exit and no flashlight strong enough to reveal what waits at the bottom. Yet total darkness does not mean nothing to see. Deeper still, in the layers where pressure and heat climb toward levels found nowhere else in the solar system, scientists believe the material itself may begin to glow faintly on its own, a dim reddish light produced by extreme heat rather than any outside sunlight at all. The same basic glow that makes a metal rod turn orange inside a blacksmith's furnace may repeat itself here, on a scale stretching across an entire planet. Nobody has ever directly observed this glow. No camera has ever survived long enough to capture it, and no probe has ever carried the right instruments deep enough to check. Every description of it remains a careful, educated guess, built from laboratory experiments and mathematical models rather than a real photograph. Your ship's external cameras struggle now, feeding back images that shift from deep blue to near black to something your instruments describe only in temperature readings rather than actual colour. Whatever glow might exist this deep sits just beyond what your current sensors can clearly confirm. That uncertainty says something important about this entire journey. Even with a real spacecraft, physically present and falling through these exact layers, some parts of Neptune's story remain locked behind instruments simply not built to see them clearly. Scientists back on Earth have to accept a strange kind of limitation whenever they study a planet this extreme, admitting openly which parts of their models rest on solid measurement and which parts still rest on careful, educated guesswork instead. The blue world you first spotted from a distance has completely disappeared by now, replaced by a blackness broken only by faint flickering readings on your dashboard. Far above you, back near the outer clouds your ship left behind hours ago, something else circles this planet quietly, a feature so faint most people never even learn it exists. Your ship's cameras keep recording anyway, capturing darkness for the sake of a complete record, since even an absence of light still tells scientists something useful about exactly how deep your ship has travelled. Saturn's rings are famous enough to recognise instantly, bright bands of ice circling the planet clearly visible even through a small backyard telescope. Neptune has rings too, and almost nobody has ever seen them. Voyager 2 confirmed their existence during its brief flyby, though ground-based telescopes had caught faint hints of something there years earlier. Brief flickers as background stars passed behind the planet and dimmed in a way plain empty space could never explain. Nobody could confirm exactly what caused those flickers until a spacecraft finally flew close enough to check directly. Those early telescope hints came from a technique astronomers call stellar occultation, watching carefully as a distant star's light briefly dims while something unseen passes in front of it. That same patient technique still helps scientists study faint distant objects throughout the solar system today, decades after it first hinted at rings circling Neptune. Neptune's rings are made from dark, dusty material, closer in colour to charcoal than to the bright reflective ice that makes Saturn's rings glow so clearly from Earth. That darkness alone makes them incredibly difficult to spot, even with powerful telescopes pointed directly at the planet. Scientists have given the rings names honouring the astronomers connected to Neptune's own discovery, a quiet tribute built directly into the structure of the planet itself. Within one of these rings, instruments detected something stranger still. distinct clumps of denser material bunched together in specific spots rather than spread evenly all the way around, like beads gathered along only part of a much longer necklace. A planetary scientist who studies ring systems once explained that most rings, including Saturn's, spread material fairly evenly around a planet over time, the same way stirring sugar into water eventually spreads it through the entire glass. Neptune's clumped rings should have spread out evenly too, yet somehow they have not, and researchers suspect the gravity of a small nearby moon called Galatea might be responsible, gently herding loose material into these tight, uneven clusters. Studying exactly how a small moon manages this kind of gravitational herding continues to teach scientists valuable lessons about ring systems throughout the solar system, including features spotted around other planets that share this same strange clumped structure. These rings also appear to be relatively short-lived, at least on a planetary timescale. Unlike Saturn's ancient, stable rings, Neptune's dark and dusty bands may disperse or break apart within a much shorter stretch of cosmic history, possibly within only a few 100 million years, a small fraction of Neptune's overall lifetime. Astronomers have also noticed the ring material appears to be slowly fading even within just the few decades separating early telescope observations from more recent ones, hinting that whatever holds these clumps together may already be losing its grip faster than anyone initially expected. Your ship's archived star charts include faint markers for these rings, invisible now from your current position deep inside the atmosphere, hidden somewhere far above the clouds you left behind hours ago. Rings this faint, this dark, and this poorly understood raise an obvious question. If material like this can gather into rings once, under the right gravitational conditions, it could happen again, especially if something much larger than dust ever found itself pulled apart by Neptune's gravity. Something exactly that large already orbits this planet right now, and its story is stranger, older, and more violent than anything discovered so far. Every large moon in the solar system orbits its planet in the same general direction that planet spins, following a smooth, predictable pattern built into the earliest days of the solar system's formation. Every large moon except one. Triton, Neptune's largest moon, orbits backward, moving in the exact opposite direction of Neptune's own spin. No other large moon anywhere in the solar system does this. That single fact tells scientists something dramatic must have happened billions of years ago, since moons simply do not form this way naturally alongside their planet. The leading explanation suggests Triton did not form around Neptune at all. Instead, it likely formed much farther out, in the same distant, icy region of the solar system, where Pluto and countless smaller frozen worlds still orbit today. At some point in the ancient past, Neptune's gravity reached out and pulled this wandering, icy world into a permanent backward orbit, a process astronomers call capture. A planetary scientist who studies moon formation once compared this event to a passing stranger getting pulled into a spinning carnival ride already in motion, forced to move against the direction everyone else on the ride is already travelling. Triton is large, nearly as big as Earth's own moon, making it one of the largest moons in the entire solar system. Finding a captured world this massive, locked into a backward orbit around a planet nearly 3 billion miles from the Sun, remains one of the strangest confirmed events in the history of our solar system. Scientists studying Triton's makeup have found its density and composition closely match Pluto and other icy worlds scattered across the distant Kuiper belt, far more than they resemble any moon that would have formed naturally alongside Neptune. That match gives the capture theory strong support, tying Triton's origin to a completely different region of the solar system entirely. Some researchers have gone even further, suggesting Triton might once have orbited the Sun directly as part of a binary pair, two icy worlds locked together the way many objects in the distant Kuiper belt still are today. Under that idea, Neptune's gravity would have needed only to break that pairing apart, flinging one icy world away into deep space while permanently capturing the other into its own orbit. Your ship's sensors, still buried deep beneath Neptune's clouds, cannot see Triton directly from this position. Yet mission files stored in the ship's memory include detailed images captured decades ago by Voyager 2, the only spacecraft to ever photograph this strange moon up close. A capture event this dramatic could not have happened quietly. Pulling a moon this large into a brand new backward orbit would have unleashed enormous amounts of energy, enough to reshape Triton completely and disrupt anything already orbiting nearby at the time. Astronomers sometimes point out that Triton and Pluto likely formed as close cousins, shaped from similar ice and rock in the same distant region of the solar system, following remarkably similar paths for billions of years before Neptune's gravity permanently separated their stories. Evidence of exactly that kind of violence still marks Triton's surface today, frozen in place for billions of years, waiting for a spacecraft close enough to read the story written across it. That kind of capture does not happen gently. Triton's icy surface still carries signs of a violent, disruptive past, cracked terrain unlike anything else in the solar system, patterns that suggest intense heating and reshaping sometime after it first arrived. When Neptune's gravity first captured Triton, the moon's orbit would have started out long, stretched and unstable, rather than the smooth, nearly circular path it follows today. Over millions of years, tidal forces between Neptune and Triton gradually squeezed and flexed the moon with every pass, generating enormous internal heat through friction, similar to how repeatedly bending a metal wire back and forth eventually makes it warm to the touch. That gradual circularizing process likely took millions of years to fully complete, a slow, violent settling in period compressed into a stretch of time far longer than all of human history combined, yet still only a brief chapter compared to the billions of years Triton has now spent quietly orbiting Neptune since. That internal heat likely melted large portions of Triton from the inside out, allowing heavier material to sink toward the center, while lighter ice rose toward the surface, a process scientists call differentiation. Evidence of this ancient melting still shows up clearly in Triton's surface today, a strange, cracked landscape, unlike anything else observed on any other moon in the solar system. Some scientists believe Neptune originally had a smaller set of regular moons, similar to the tidy, well-behaved moon systems circling other planets in orderly, predictable orbits. Triton's violent arrival likely shattered or scattered that earlier system completely, flinging smaller moons into new orbits or destroying them outright during the chaos of capture. A planetary geologist who studies Triton's surface once compared the moon's cracked, unusual terrain to a plate of ice that had partly melted and then refrozen unevenly, leaving behind ridges, cracks, and strange patterns that do not match any simple single explanation. Very few craters mark Triton's surface compared to other icy moons of similar size, a strong clue that its surface has resurfaced itself sometime in the relatively recent past, geologically speaking, covering over older impact scars with fresh material from below. Scientists estimate parts of Triton's surface may be no older than a few 100 million years, remarkably young for a moon that formed billions of years ago. Your ship's archived images show wide, dimpled plains stretched across parts of Triton's surface, nicknamed cantaloupe terrain by the scientists who first studied them, since the pitted texture resembles the skin of the fruit more than anything typically seen on a frozen moon. Voyager 2 only managed to photograph less than half of Triton's total surface during its brief flyby, leaving the rest of this strange, cracked world completely undocumented to this day. Whatever additional evidence of that ancient violence might exist on the unseen half remains as much a mystery now as it was decades ago. Whatever violent history shaped Triton billions of years ago, that story did not end once the moon settled into its current orbit. Something inside Triton has stayed active every single day since, defying the extreme cold that should have frozen this entire world into complete silence long ago. Triton's surface sits at a temperature close to negative 390 degrees Fahrenheit, one of the coldest surfaces ever directly measured anywhere in the solar system. At temperatures that extreme, even nitrogen, the gas that makes up most of Earth's own atmosphere, freezes solid into ice and frost coating the ground. Despite that brutal cold, Voyager 2 spotted something nobody expected during its brief flyby: dark plumes rising directly from Triton's frozen surface, stretching miles into the thin, weak atmosphere above. Scientists quickly recognized these as geysers, similar in basic concept to the geysers found in places like Yellowstone back on Earth, except powered by an entirely different, far colder process. Yellowstone's geysers erupt when underground water heats up and turns explosively to steam. Triton's geysers involve nitrogen instead of water, likely triggered by a strange effect scientists call solid-state greenhouse warming. Sunlight, even the extremely weak sunlight reaching this far from the sun, can pass through a thin, clear layer of surface ice and warm a darker layer of nitrogen trapped just beneath it. That trapped nitrogen slowly builds pressure as it warms, sealed beneath the ice above it, until it finally bursts through in a sudden, forceful eruption, carrying dark dust and gas high into Triton's thin atmosphere, before drifting back down and settling into long, dark streaks across the ice. A planetary scientist who studies icy moons once compared this process to shaking a sealed bottle of soda left sitting in weak winter sunlight, pressure building slowly and quietly for a long stretch of time before finally releasing all at once, in a sudden burst nobody standing nearby would have predicted. Voyager 2 captured images of several active plumes during its short visit, direct evidence that Triton remains geologically active today, despite sitting at one of the coldest, most distant points in the entire solar system. Few other worlds this far from the Sun have ever shown this kind of ongoing activity. Winds high in Triton's thin atmosphere appear to bend these dark plumes sideways as they rise, stretching each eruption into a long drifting streak rather than a straight column, evidence of weather patterns quietly at work on a moon most people assume should be too cold and too still to have any weather at all. Your ship's archived data includes measurements, suggesting these eruptions might follow a seasonal pattern, tied to Triton's own extremely slow orbit and Neptune's own decades-long seasons, meaning the geysers active during Voyager 2's visit might behave completely differently today, decades later, as sunlight angles have shifted across the moon's frozen surface. Nobody has confirmed that pattern directly. No spacecraft has ever returned to check. Cold, distant, and still surprisingly active, Triton already stands apart from nearly every other moon in the solar system. Yet its geysers are not even the strangest thing happening to this moon right now. A handful of researchers have even suggested Triton's plumes could eventually help a future mission study the moon's subsurface composition directly, sampling material launched naturally into space, rather than requiring a lander to drill through solid ice. No mission has ever attempted this, but the idea remains an intriguing possibility for whichever spacecraft eventually returns. Something slower, quieter, and far more permanent is happening to Triton's orbit itself, a process already sealing this moon's eventual fate. Every moon eventually settles into a stable, lasting relationship with the planet it orbits, circling steadily for billions of years without much change. Triton is a rare exception, and the reason traces directly back to its strange backward orbit. Because Triton orbits in the opposite direction of Neptune's spin, gravity between the two worlds works against the moon instead of supporting it. Tidal forces, the same basic pull that creates ocean tides on Earth, slowly drain energy from Triton's orbit with every single lap around the planet, pulling the moon gradually closer to Neptune over enormous stretches of time. Scientists have measured this slow drift directly, comparing Triton's exact position today against calculations of where it should be if its orbit stayed perfectly stable. The moon really is spiraling inward, moving closer to Neptune bit by bit. in a process too slow to notice within a single human lifetime, but unmistakable once tracked across decades of careful observation. Every other large moon in the solar system slowly drifts away from its planet rather than toward it, gaining energy from tidal forces instead of losing it. Triton's backward orbit flips that entire relationship, making it one of the only large moons anywhere guaranteed to eventually meet a violent ending rather than settling into permanent peaceful stability. A physicist who studies orbital mechanics once compared this slow spiral to water gradually circling a drain, invisible movement at any single glance, yet unmistakable and irreversible once enough time has passed to reveal the full pattern. That comparison only goes so far, since a draining sink empties in seconds, while Triton's spiral will likely stretch across several billion more years before finally reaching its end, a timescale so long it barely fits inside any comparison drawn from ordinary human experience. Current estimates suggest Triton could continue this slow spiral for several billion more years before finally reaching a critical distance from Neptune, a boundary scientists call the Roche limit, the point where a planet's gravity grows strong enough to overpower a moon's own internal structure completely. Nobody alive today, and nobody born for countless future generations, will ever witness what happens when Triton finally crosses that boundary. This process unfolds across a timescale that dwarfs the entire history of human civilization many times over, a slow countdown that started long before humans existed and will likely finish long after everything we currently know has faded into history. Your ship's onboard files include long-term orbital projections calculated by scientists studying Triton's decline, models built from careful mathematics rather than direct observation, since no human being will ever live long enough to watch the ending unfold in real time. Triton remains for now a moon quietly living on borrowed time, active with icy geysers, frozen in extreme cold, and slowly falling toward a planet it was never originally born around in the first place. Some researchers studying this slow decay have compared Triton's fate to a satellite in low orbit around Earth, gradually losing altitude to friction until it finally burns up. Triton faces no air resistance out here in the emptiness of space, yet gravity works against it just as relentlessly, patient enough to finish the job across billions of years instead of mere decades. That slow fall will not end quietly. When Triton finally crosses that critical boundary, Neptune's gravity will not simply pull the moon in gently, it will tear the whole moon apart. When Triton finally crosses close enough to Neptune, gravity will not act evenly across the entire moon at once. The side facing Neptune will feel a noticeably stronger pull than the side facing away, and that difference in force is exactly what tears a moon apart. Scientists call this boundary the Roche limit, the precise distance at which a planet's gravity overpowers the internal forces holding a smaller body together. Cross that line, and a solid moon stops behaving like a single object entirely, stretching first, cracking next, and eventually breaking into countless smaller pieces scattered across a wide, shifting band. Icy bodies like Triton tend to break apart more easily than rocky ones, since ice holds together with far less internal strength than solid stone. That weakness means Triton's eventual destruction could unfold somewhat more gradually than a similar event involving a rockier moon, stretching the process across a longer, messier collapse rather than one single, sudden break. This is not simply theory built entirely from imagination. Astronomers have directly observed similar events happening to smaller objects elsewhere in the solar system. Comets torn apart after passing too close to a massive planet, breaking into a visible chain of separate fragments still travelling roughly along the same path. Triton would face a similar fate, except on a scale far larger than any comet ever recorded breaking apart. A planetary scientist who models moon destruction once compared the process to squeezing a snowball slowly tighter and tighter in one hand. At first, the shape holds, then cracks spread across the surface. Finally, the whole thing crumbles apart at once, scattering fragments in every direction, rather than holding together as a single solid mass. The exact moment this begins would likely unfold gradually rather than instantly, stretching across thousands of years as Triton's orbit tightens closer and closer to the breaking point, rather than a single dramatic instant captured in one violent flash. Because Triton is large, nearly the size of Earth's own moon, its eventual destruction would release an enormous amount of icy, rocky material directly into orbit around Neptune, far more raw material than any other moon breakup ever recorded or predicted anywhere in the solar system. Your ship's projection models estimate this event still lies billions of years in the future, far beyond any timescale relevant to your current mission, yet the ship's systems continue tracking it anyway, logging every detail available as part of a complete scientific record. Nobody will ever witness this moment directly, not with current human lifespans, not with any technology currently available or reasonably imaginable. Whatever future intelligence eventually observes Triton's destruction, whether human or something else entirely, will witness something no telescope has ever directly recorded happening to a moon this large. The debris left behind will not simply vanish into empty space. Trapped by Neptune's gravity, every fragment will begin circling the planet instead, joining together into something entirely new. Scientists who model this kind of destruction point out that the exact outcome depends heavily on how close Triton sits to the Roche limit at the moment it finally breaks apart. A slightly closer approach could grind the debris into extremely fine dust. A slightly farther approach could leave behind larger, more substantial chunks, closer in size to small moons themselves rather than simple grains of ice. Given enough scattered ice and rock circling a single planet, there is only one shape that material naturally tends to form. Picture every fragment of a shattered moon nearly the size of Earth's own moon, scattered into a wide band circling Neptune. That much material, held in place by gravity, and stretched into a thin, orbiting ring, could create something far more dramatic than anything currently visible around this planet. Saturn's rings, the brightest and most famous in the entire solar system, are built mostly from countless small pieces of bright reflective ice, likely the remains of a shattered moon or comet from billions of years in the past. Triton's eventual destruction could create a similar ring system around Neptune, except built from a single source object far larger than anything scientists believe originally formed Saturn's rings. Astronomers studying Saturn's rings still debate exactly how old that system really is, with some evidence suggesting it formed relatively recently on a cosmic timescale, rather than alongside Saturn itself billions of years ago. A future Neptune ring system, born from Triton, would settle that same kind of age question immediately, since scientists would know its exact starting point down to the year. A planetary scientist who models ring formation once explained that ring size depends heavily on the size of whatever object gets torn apart to create it. A small, shattered moon produces a small, thin ring. A moon the size of Triton, nearly matching Earth's own moon, could theoretically produce rings wide enough and bright enough to rival or even surpass Saturn's current display, depending on exactly how the debris eventually spreads and settles into place. Nobody can predict the outcome with full certainty. Some models suggest the debris might spread thin and dim over time, fading slowly the same way Neptune's current faint rings appear likely to fade. Other models suggest a large enough source moon could create something bright and stable enough to remain visible for a significant stretch of time afterward, an entirely new visual signature stamped permanently onto this distant planet. Your ship's projection files include several competing models built by different research teams, each offering a slightly different picture of what a post-Triton Neptune might eventually look like. None of these models has been tested against real data, since no ring system this large has ever formed from an object this massive within recorded human history. Whatever future scientists eventually witness, if humanity or its descendants still exist billions of years from now, Neptune could someday transform from a planet known mostly for its faint hidden rings into a planet known for something spectacular circling it instead, born from the same moon currently spiraling quietly overhead. For now, none of that has happened yet, Triton continues orbiting steadily above, its icy geysers still firing, its slow spiral still measured in mathematics rather than direct observation. A handful of astronomers have started referring to Triton as a ring system still waiting to happen, a striking way of describing a moon whose eventual fate already seems locked in, even if the exact timeline and final appearance remain impossible to predict with full certainty. Your ship continues falling in the opposite direction entirely, deeper into a planet already hiding enough mystery to fill lifetimes of research, without ever needing to wait billions of years for a moon to break apart. Somewhere below, in the crushing layers your ship has not yet fully explored, an even stranger question waits, one that reaches far beyond storms, rings, and moons entirely. Deep inside Neptune, in the layers your ship is currently pushing through, conditions include liquid water, carbon, nitrogen, and intense heat. The same basic ingredients scientists associate with the earliest chemistry, believed to have sparked life on Earth billions of years ago. That overlap has led some researchers to ask a careful, open question. Could a layer like this, buried deep inside an ice giant, host the kind of basic chemical building blocks connected to life, even if actual life itself remains extremely unlikely to exist here? The pressure and heat inside this layer far exceed anything any known organism on Earth has ever survived. Even the toughest microbes discovered thriving near deep-sea volcanic vents on our own ocean floor. Those extreme organisms, sometimes called extremophiles, already push the boundaries of what scientists once assumed life could tolerate, surviving crushing pressure and scorching heat far beyond anything found near Earth's surface. Researchers studying Earth's own deep-sea vents continue to be surprised by how far the boundaries of survival can stretch, discovering new extremophile species in conditions once assumed to be completely lethal. Each new discovery quietly shifts the line scientists draw between where life can and cannot possibly exist. A biochemist who studies the origins of life once explained that the building blocks of life and life itself are not the same thing at all. Water, carbon, and energy can combine and react in complex ways without ever producing anything resembling a living organism. Neptune's interior might host fascinating chemistry, without hosting biology of any kind. Still, the question keeps researchers interested, since ice giants like Neptune are common throughout the galaxy, far more common than planets similar to Earth. If basic prebiotic chemistry can occur naturally inside a world like this one, similar processes could theoretically be unfolding right now inside countless other ice giants scattered across the universe, hidden beneath clouds no telescope will ever fully see through. Your ship's instruments, built primarily to study pressure, temperature, and structural readings, were never designed to search for signs of biology directly. Still, sensors continue logging the exact chemical composition of every layer your ship passes through, data that future scientists could eventually study for clues nobody currently knows how to look for. Nothing detected so far suggests anything resembling life exists inside Neptune. The pressure alone would crush any structure remotely similar to a living cell, long before heat or chemistry ever became a relevant factor. Yet the fact that scientists can even ask this question honestly, about a planet nearly 3 billion miles from the nearest source of life anyone has ever confirmed, says something remarkable about how far understanding of the universe has already travelled. Some researchers argue that ice giants like Neptune deserve far more attention in the search for life beyond Earth than they currently receive, since most search efforts today focus almost entirely on smaller, rocky worlds instead. A planet like this one, common throughout the galaxy yet still barely explored, might be quietly overlooked, simply because reaching it is so difficult. Your ship pushes even deeper now, past layers where questions about life quietly fade, replaced by a far more immediate and personal question. Whether any spacecraft, carrying any kind of equipment at all, could survive long enough down here to send anything useful back to the people who built it. Surviving Neptune's crushing depths means nothing if a spacecraft cannot also send its discoveries back home before being destroyed. Every mission ever proposed for this planet has to solve both problems together, survival and communication, at the exact same time. The clearest example comes from the Jupiter probe mission decades ago, the closest comparison scientists have for a Neptune atmospheric descent. That probe never tried to communicate directly with Earth during its brief fall. Instead, it beamed its readings to a parent spacecraft waiting safely in orbit above, which then relayed everything back home once the dangerous part of the mission had already ended. A future Neptune probe would likely need the exact same setup, a larger spacecraft remaining safely in orbit far above the crushing depths, acting as a relay station for a smaller probe sent down into the atmosphere alone. Direct communication from deep inside Neptune straight back to Earth would be nearly impossible, blocked by thick layers of gas, extreme pressure, and a communication delay already stretching past 4 hours in each direction, even under ideal conditions. Engineers have to account for that same 4-hour delay, even between the probe and its own parent spacecraft waiting in orbit, since even a short relay distance still demands careful timing, with every command and every burst of data scheduled well in advance rather than reacted to as it happens. Every second of survival time inside the atmosphere becomes precious under this kind of setup. Engineers have to carefully plan exactly what data a probe should prioritize collecting first, since a mission that survives only a short while cannot afford to waste time on anything except the most valuable readings available. Some proposals suggest transmitting data continuously throughout the descent rather than waiting until the very end, ensuring that even a sudden, unexpected failure partway through would still leave behind a partial record rather than losing everything at once in a single final moment. A mission planner who worked on the Jupiter probe once explained that engineers accepted the mission's end from the very beginning, designing every system around a guaranteed, permanent loss of contact rather than any real hope of long-term survival. Success meant collecting and transmitting as much valuable data as possible before that inevitable end arrived, not surviving indefinitely against impossible odds. Your ship faces that exact same reality right now. Every reading collected since the descent began has already been logged, and whatever happens next, that data represents this entire mission's true and lasting achievement. Structural warnings continue flashing steadily across your dashboard, confirming what every previous chapter of this journey has already suggested. No spacecraft, current or currently imaginable, could survive Neptune's deepest layers indefinitely. Success here was never about reaching the bottom. It was always about how much could be learned and transmitted safely home before the pressure finally wins. Real mission planners accept this trade-off openly rather than treating it as a failure. A short burst of real data from an entirely new environment is worth more to science than a mission that never launches at all, out of fear of an inevitable ending. Your ship's transmitter activates one final time, sending everything collected so far racing outward through the darkness toward a destination nearly 3 billion miles away. What happens next has never been witnessed by human eyes, not once, not ever, in the entire history of space exploration. The pressure gauge on your dashboard stops climbing in smooth, steady increments and begins jumping instead, numbers spiking upward faster than the display can properly track. Outside your hull, the ocean that once stretched endlessly in every direction has grown denser still, thickening towards something that barely resembles liquid anymore, pressed by weight from thousands of miles of planet stacked directly above it. Your ship's outer plating groans one final time, a deep resonant sound different from every warning heard so far during this entire descent. There is no violent explosion waiting at the end of a journey like this one. Engineers who study extreme pressure environments describe a much quieter, steadier kind of ending, a slow, continuous crushing as material presses inward from every direction at once, faster than any structure could ever hope to resist or repair itself. Communication systems flicker one last time, straining to push a final signal outward through crushing layers of compressed gas and liquid. That signal, carrying every reading your ship has collected since the very beginning of this descent, races upward and outward, gaining speed as it clears the thickest layers and finally escapes into open space. From there, it travels alone, crossing nearly 3 billion miles of empty darkness at the fastest speed physics allows, carrying proof that something built by human hands once reached farther into this planet than anything ever had before. A researcher who models deep planetary environments once said that any spacecraft attempting this kind of descent is not really trying to survive Neptune at all. It is trying to outrun the inevitable for just long enough to matter, gathering as much knowledge as possible before physics finally closes the gap completely. Your ship's instruments record their final readings in the last fraction of a second before pressure overwhelms every remaining system at once, numbers climbing off the scale entirely, sensors going silent one after another in rapid succession. Somewhere far above, back near the storms, the diamonds and the electric blue clouds where this journey first began, none of that violence ever reaches the surface. Neptune continues spinning exactly as it always has, storms raging, winds howling, seasons creeping forward at their own impossibly slow pace, completely indifferent to the small, brief visit that just ended somewhere deep inside it. Nearly 4 hours later, a faint signal finally reaches Earth, carrying the last transmission ever sent from inside an ice giant. Proof that for one brief moment, humanity reached farther into the outer solar system than ever before. Somewhere in a control room back home, a small group of scientists watches that signal arrive. Decades of patient waiting compressed into a single quiet moment. Nobody else on the planet is watching alongside them. There is no cheering, no dramatic countdown, only the steady blink of data finally completing a journey that began long before it ever launched. Every number in that final transmission becomes the beginning of a new chapter in what humanity understands about ice giants generally, every similar world scattered across the galaxy waiting quietly for their own turn to be explored. Neptune keeps its secrets well. For a few short hours, one small spacecraft managed to learn a handful of them anyway,